Great. So we'd like to welcome everyone here. And we're really excited today to have another Stephanie here, Stephanie Wall. But before we get started, we would like to acknowledge with respect the Lekwungen-speaking peoples on whose traditional territory the university stands, and the Songhees, Esquimalt, and Wasatch peoples whose historical relationships with the land continues to this day. So our speaker today is Stephanie Wall. Stephanie, come on up. And Stephanie received her undergraduate degree in environmental engineering, and that was a joint degree between UNBC and University UBC, UBC Vancouver campus. And so after completing her undergraduate degree, she then enrolled in and completed a master's degree in the Engineering and Integrated Wood Design program at UBC, and that was the first cohort to go through there, as I understand. And she's currently employed as a structural engineer in training, is that right? With McCollany,
yeah.
Thank you, Consulting Services in Prince George. And so today she's here to talk about a very exciting project at UNBC. It's in part funded by PICS. At the Wood Innovation Research Laboratory there. And she will be discussing wood construction and passive house design to decrease the greenhouse gas emissions and environmental impacts of industrial buildings. So I'm very excited to hear her talk. I was involved in hearing about the ideas that came forward in the start of this almost a couple of years ago now. So it's very exciting. It'll be very exciting to see the progress on this project. And I'll turn it over to you, Stephanie.
Okay.
And let's see, you're already mic'd up.
I think so, yeah, so we're good.
Good.
Thank you, everybody, so much for your attention. I hope it'll be of interest, and I did want to take a second to thank PICS for hosting. And yeah, we'll just jump right in. So as she already introduced, I'm going to go over today a comparative LCA that I conducted on the Wood Innovation Research Lab. And this was done last year. I was employed by UNBC to conduct this study. And the reason why this building is of interest is it's an industrial building located in Prince George, BC, which is a relatively cold climate. So the building is designed with wood. We've got a glulam post and beam superstructure. And it's designed to passive house standards, which is really challenging for a building of this occupational type, and we'll dive into some of those details later. So as was already introduced, I just wanted to go over kind of what brought me here today and why I've been interested in green building design. I did my bachelor's degree in environmental engineering, and during that time, you really get quite familiar with what the problem is, and you understand the magnitude of the mess that's out there and how humans can have such a detrimental impact on the environment through many different processes. And you learn the technical solutions and how to engineer and remediate different sites and different projects. But at the end of that, I wanted to be on the preventative end of things. And as we all know, buildings in the construction industry can have a huge impact on the environment. It's a huge consumer of our natural resources, and during every phase of the life cycle, it produces emissions. So I was interested in how we could improve that demographic of the construction industry, and this led me to the Integrated Wood Design program, which I will also tell you a little bit more about because I think it's a fantastic program, and this is a great opportunity to tell people about it. So just a quick outline for our presentation today. I'm going to talk about buildings in the context of the environment. I'm going to introduce LCA because I'm not entirely sure the background of everyone here. We'll talk a little bit about the project context for the Wood Innovation Research Lab. And I'm going to introduce Passive House Standard for those who aren't familiar and talk about the results of our project and the results of my LCA. So buildings in the environment. This slide is a little hard to read, I apologize. But essentially, the built environment accounts for 17% of BC's total CO2 emissions. And BC has made it a mandate to reduce our emissions by 80% of the 2007 levels by 2050. So that's a pretty hefty target, and I think each industry needs to evaluate how they can contribute to that. So what makes a building green? And I have to admit that up until 2 years ago, this was, and still is, I think, can be quite an ambiguous and vague topic. So you definitely are introduced to a lot of different green labeling out there. There's LEED, Passive House Living Building Challenge. And also, if you're discussing green buildings, you're going to get into the specifics of different green components. So a building might be green because it has a green roof, or it has solar panels or PV. So I wanted to know, how do we really compare? What truly is a green building? And sometimes it can feel a little bit like comparing apples to oranges. You know, one building might have great accessibility and walkability, but it's all glass and consumes a lot of energy during its operation. So life cycle assessment is a scientific basis for comparison of simple products, such as apples and oranges, all the way up to complex systems like a building. So I applied the life cycle assessment methodology to look at green buildings. Now, for someone like me who's kind of been studying this for a year, when I look at a building, I can kind of picture the different steps in its life cycle and think about what emissions and what impacts those steps have. But for anyone who's not in that background, I've just put up a couple pictures that I hope will just be provocative to kind of get your mind thinking about, okay, when we look at a building and we're trying to determine how green it is, these are some things to consider. So we'll start with, what raw materials go into the building? Is it wood? Is it concrete? Is it steel? How are those different materials extracted? How much energy does it take to extract them? And then the manufacturing of those raw materials, how much energy goes into that process? What are the byproducts? Transportation, is it a local material? Is it imported? Does it arrive by boat, or are we hauling it long distances on a vehicle? During the actual construction of a building, are we using a crane on site, or is it mostly manpower? And then during the use, the maintenance, the repair, and the renovation of a building, I have here, just to explain a little bit, we've got a thermal image of a building. So during the operation of a building, there's heat losses, because we want to keep our environment in the building, usually during the winter, warmer than outside, and during the summer, cooler than outside. And there's losses involved with that. There's also emissions. I've got pictured here UNBC's bioenergy plant. And even though that's a green source of fuel for the buildings on campus, there are still emissions associated even with that clean fuel. And then at the bottom, we've got our repair and renovation. So once the building is constructed, that's not the end of the story. There's still going to be repair and renovation over the building life, and that's going to need additional material. And there's going to be waste that we're going to have to either dispose of or recycle. Which brings me to the last end of a building life, which is our disposal and recycling. So when we're talking about two different buildings and we're trying to compare how green they are, this is an important consideration, because even though a building might have recyclable materials, you still have to ask the question of, where's the building located and what kind of facilities are available to deal with these materials. So these are the questions that definitely will come up when you're talking about and comparing green buildings. So now I'll talk a little bit more specifically about our green building at UNBC, which is our newly constructed Wood Innovation Research Lab. So there, as I mentioned, UNBC for 3 years now has had a Master's of Engineering in Integrated Wood Design program. This program covers the structural design of tall wood structures, seismic design, mixed structures, so how wood can work with steel and concrete in a way that makes sense. Building physics, so energy efficiency, the envelope, protecting a building and its structure from water ingress. Sustainability, what kind of materials are we going into a building and what are their impacts? And then processing, so what goes into the manufacture of engineered wood products and how can we better utilize those in our buildings? So this program is intended to have eventually 20 students. I was in the first cohort and there were 4 of us, and it's slowly growing, but hopefully it will continue to grow. But one limiting factor is that the lab space, which is in the bottom of the Wood Innovation Design Center, pictured here, is just simply too small. When I was in the program, there were 4 of us, and I felt at times like the lab was utilized at capacity when we were all in there working on our different projects. So it was identified as a need that if the program was going to continue to expand, that we were going to need some more lab space. So the Wood Innovation Research Lab was the solution to that. Just a couple quick facts about it. It's just over 1,000 meters square in footprint. It's a single story, so 10 meters tall, with a mezzanine. It has a strong wall and strong floor, which is essentially a giant concrete wall and concrete floor with large capacity so that we can attach wood structures in the future and do some seismic testing on those. There's a wood conditioning room, which allows wood samples to reach a proper moisture content over time so that your tests on wood is consistent. It was identified as a need to have a seminar space for 30 students or guests to the Wood Innovation Building, 3 office spaces for the technicians, and a dust extraction system. So the project scope, it was a $5.32 million budget, and this project was partially funded by the federal government and the provincial government, as well as the city of Prince George provided the piece of land that it was constructed on. And it's designed kitty-corner to the existing Wood Innovation Design Center, so it's a short walk for the students to the new lab building. The timeline for the project was, the project team was officially assigned the project in March, and they were given until the end of this month to complete construction, so quite a concise and short timeline. It was required to be wood design and to meet Passive House certification. Now, this was unique for this project because in the past, UNBC has required that buildings are designed to LEED standard, and this was the first Passive House building. Just a couple notes, too, about why this building is innovative. There's over 4,000 Passive House projects registered in the Passive House Institute's database, and of those, there's only a handful that are industrial buildings. And there aren't any in North America. So this will be the first one in North America that reaches this standard. What is Passive House standards? Well, it follows a few key principles. You want to design a building that's compact, really well insulated, has no air leakage, so a good airtight layer. You want to minimize the thermal bridging through corners, through windows, through doors. You need efficient glazing, so triple pane is usually what you would see in a passive house. And you need effective ventilation. When you have such an airtight building, you need to maintain air quality, and you don't want to lose heat with your air that's being lost to the outside. So a passive house project usually requires a heat recovery and ventilation system. So for those who are a little bit more visual, I like to describe Passive House standard as basically you need a really good coat on your building. So you start with your base layer, which is your moisture control, and then you need your middle layer, which is going to be your thermal layer, and then you need your windbreaker, and that protects you from wind and rain and air coming in and out. And then I think, too, what is perfect about this analogy is you can put that setup on a mannequin, and it's not going to keep the mannequin cold or warm. It's not going to have any effect because you need something that generates its own heat. And in a passive house project, that's actually the occupants of the building, or it's the small pieces of machinery that might be running, or it's the light bulbs. It really all adds up to be quite a significant source of heat when the required heat is so small. So for those who are a little bit more familiar, these are the targets for Passive House standard. And what makes this standard difficult to achieve, especially in a place like Prince George, is that it doesn't change according to your climate. The standard stays the same. And so it can be difficult to achieve when you do have such a dominant heating location. So you're limited to 15 kilowatt hours per meter squared per year. And this is what made the lab building so challenging, is it's on a per meter square basis. And we've got a building that is a really big volume with a really small footprint. It also limits the heating and cooling load, the thermal performance of the envelope, It needs to be thermal bridge free. So there's a way to calculate that using their passive house planning package. You can look at the windows and all the detailing. And it also provides additionally thermal comfort in both the winter and summer. So challenges that were specific to our project I've already touched on, but we have a cold climate rating in Prince George. We've got a high volume to treated floor area ratio. And as with most industrial buildings, it's required to have an overhead door so that you can have materials easily being brought in and out. And these are not standard to be very airtight or to be very well insulated. So we actually had to custom order a door that has rubber gaskets that we can fit snug to the envelope and make sure that we maintain our airtight barrier. And then another challenge is that we had limited local prefabrication industry. So we are having 10-meter wall panels, and they're over 500 millimeters thick with insulation, so they're hefty. And we wanted these originally to be prefabricated and delivered to site so that they could be craned into place, and it would be, a smooth transition. Everything would stay dry. But there just simply wasn't a facility, a local facility that could do that. What we did have was a facility that could provide the framing for the walls and the sheathing and the vapor barrier. And then those panels were brought to site, craned into place, and we ended up actually insulating on site from the bottom up. And I'll show a couple pictures. But yeah, that was definitely a significant challenge for this project. So a few photos. This is the concrete delivered to site for the concrete strong wall and floor. Sorry, it's on an auto timer here. When I did my LCA, just a little side note, this was definitely a hot spot, meaning it accounted for over 30% of our total environmental emissions. The concrete in the strong wall and floor, not including the foundation, just that one piece of equipment, which is pretty hefty. Yeah, so this is just a photo from the inside. We've got our glulam column and beam, and we've got our wood truss ceiling. This is one of the panels being craned into place. You can see we're doing it in the dead of winter because of our tight timeline. And then I don't know if you can see, but in the bottom half of the picture, you can see someone, he has the blown-in insulation going into the wall. So where's the project at today? We recently had our final measurements to achieve our Passive House certification. And we did our blower door test, which tests the airtightness of the building. And if you remember in a previous slide, that target for Passive House is 0.6 air changes per hour at a pressure of 50 pascals. And our blower door test came in at 0.07. So that's significantly above our target, which is great because we can now go in and reiterate the Passive House certification and design, and it really does lower our operational energy and our heat. Because of the change in the way that we insulated the walls, instead of being insulated in the shop, the walls were insulated on site. We actually ended up having a denser pack to our insulation, which in the end provided us with slightly higher thermal values than we were expecting as well. So there was an incredible attention to detail, and the project team really delivered on what we were aiming for. So the official opening of this building is this coming Tuesday, and everything was finished on schedule, which is fantastic. And I was recently talking with my colleague, and he was saying that the construction team that was on it, they're already being slated for potential future projects because they have that experience. So a building like this isn't just a learning experience for academia. It's definitely a learning experience, and it adds value to the industry. So now we're here to talk about the LCA that I did on this building. So the question that I was really interested in answering for this project was to isolate the effect of our material and the embodied energy versus the operational energy. Because if you think about it, if you're trying to increase the energy efficiency of a building, you're going to add material. And what's the effect of that? And some people even question, is there a net positive effect if you're putting so much insulation, or you're filling the base with this thick EPS on the roof and below the slab? So I wanted to look into that. And I also wanted to compare just the magnitude of effect. If you do have a really efficient home or building, then how significant is that material? Because it's going to be a much smaller piece of the puzzle. So we were going to have a look at that. And what makes this kind of interesting is if you do this for one building and you vary the structure or the design standard, you keep all the other variables the same, which really makes it quite clear. Because if you're comparing two buildings as built, two buildings that have actually been constructed, there's going to be other factors at play, like what the local building codes were at the time of design, the orientation of the building, the local climate, all of these different things that play a factor. Whereas for this project, we were really able to isolate the effect of changing the material in the structure and changing the design standard and keeping everything else the same. So I created 4 models to compare of the same type of building. One was the Wood Innovation Research Lab as built, which is wood to Passive House standard. But then I also did wood and had it designed to code, and with steel to code and steel to Passive House standards. So the methodology, I use the Athena Impact Estimator for buildings, which is an excellent tool. It uses the Tracy database for the indicator values, and it's based upon the ISO 14040 standard. The functional unit for this comparison was one 30 by 30 industrial building located in Prince George, BC, with a 60-year service life. And just a little note on some of my key learnings from this project and some of the things that I took away. I have this diagram here of my process. So first I went through and I created my models. Obviously, only one of the models was actually built and constructed. So it had a complete materials list, but the rest of them were more or less from my imagination, and I had to design according to the different standards. So you have to create the material list for the 4 models that you're comparing. And then you generate the energy model using PHPP. So if you designed it to code, it's going to have a different energy consumption than if you've designed it to Passive House standard, and you need a number for that. And then you take the material lists and your operational energy, and you put that into Athena, and sometimes you have to find the material equivalent. Athena has a limited database. So that was a bit of my process and my challenge. So a little bit about creating the material list for the Wood Innovation building as built. Since this is not super commonly done in industry, it's becoming more common because code in Vancouver is officially requiring LCAs to be done for some new construction projects, as I understand. But in the past, this is definitely a new concept. And so when I went to gather my materials list, it wasn't as simple as I thought it would be. I had from the local prefabrication facility who was doing the wall panels, they had a CADWorks file for me, which is a 3D file. And then I went to the structural engineers, and they provided me with some 2-dimensional drawings with some callouts. And then I went to the architects, and they had a Revit model, which included some more of the materials that I needed. So this was definitely a challenge to put all these pieces of the puzzle together to get a complete material list. And just on a side note, this is a topic for another time, but building information modeling definitely will assist in the future if we're creating consistent 3D models that everybody who's involved on the project team contributes to. Then an LCA will simply be just one additional step to that, where you take that materials list and you plug it into the Athena Impact Estimator or equivalent, and it's going to be a much more streamlined process. So the Athena Impact Estimator produces indicator categories, and instead of going through all of them, because the buildings are going to be compared and they're going to look slightly different depending on the unit of comparison, for the future slides, I'd like to highlight that I'm talking about global warming potential, which is CO2 equivalents. So what did my models look like? My wood model, we had glulam columns and beams, concrete raft slab, which was the same for the wood and the steel. I had wood TJI joists for the floor systems and trusses for the roof and for the walls. And the steel model, I had wide flange steel for the columns and beams. The foundation, once again, stayed the same. And then open web steel joists for my roof and for my flooring systems. And one thing that I'd really like to highlight as well is I have a slide in the future that has my graphs and we can see the direct comparison. Something's a little bit off if you pay close attention. And that is because my steel model for my passive house design includes wood exterior walls. And the reason for that is because it's almost impractical to design such a high efficient building when you have thermal bridges in your structure protruding through your envelope. So that model, my steel to passive house, has wood walls, but this superstructure is steel. So some differences between our to code models and our passive house models: significantly less insulation in the foundation and on the roof, less insulation in the walls. Our windows for the code models were double pane. We didn't have any heat recovery, and we didn't